Today, what we'll look at is the proof of existence of infinite family of bipartite Ramanujan graphs for every degree D. So the first question is, what is a Ramanujan graph? And this is the result of Adam Marcus transform and transform. So this will take us, I think, a couple of classes at least, slightly more than that. Even with all the stuff we've already done. So, but first, what is a Ramanujan graph? So the goal is to let G be a an undirected regular graph of degree D, let's say. Okay, so it has a symmetric adjacency matrix A, right? And because of symmetry, so A has real eigenvalues. Okay. And so because of symmetry, so it has real eigenvalues. And so first question is, what is the largest eigenvalue of A?
It's D regular, right?
Yeah.
So D.
Yeah, right. So and even if it is not D regular, it's maximum degree D, still the maximum eigenvalue cannot be more than the maximum degree.
Right.
So yeah. So okay. So let's so easy to show. Easy to show that for a graph of max degree D, delta lambda max of A has to be bigger than the absolute value of lambda max of A, or rather the maximum absolute value of any eigenvalue is less than equal to that. So this is not hard, and so for D regular graph, you can actually get equality easily. D regular graph. Just take A1 is equal to D. So maximum eigenvalue is D. And now the interesting thing becomes, so okay, so this is fine. So the interesting thing becomes is what is the just define this term first. Let's see why the spectral gap is defined as the following. So take the eigenvalue of A that is so drop the eigenvalue D, right? And among the remaining eigenvalue, which one of them might actually be equal to D also, so you see, and among the remaining eigenvalues, let lambda be the eigenvalue of maximum possible absolute value. Okay, so spectral gap is defined to be, so sometimes it's defined slightly differently, but I'll just define it as just D minus so in particular, if most of you might have seen that if the spectral gap is 0, which means that the eigenvalue D is repeated twice, at least twice. is equivalent to the graph being not connected. Okay. So the point is that this only happens if the graphs, the agency matrix breaks into two block matrices, and each one of them individually has the all ones eigenvector. Okay, so the point of this, the spectral gap seems to have something to do with connectivity, and also actually a lot to do with connectivity. So the spectral gap being bounded away from zero is essentially equivalent to graph expansion. Okay. So without dependence on where FD is sort of does not depend upon the size of the graph. Is one of the natural definitions of graph expansion. Yeah, one of the natural definitions of graph expansion. And what is graph expansion? Graph expansion is a property that if you take any subset of the vertices, then somehow, and you look at all the edges going out, then a large fraction of the edges that are incident on these vertices actually goes out of that set of vertices. So I will not define it more formally, but because we'll only deal with the spectral wording. So, but for now, but just to review, let's just recall that the spectral gap being bounded away just as a function of the degree and not as a function of the size of the graph is one of the standard notions of expansion of a graph family. So if you have a family of graphs all with degree fixed, and then as the size grows, if the spectral gap remains bounded away from zero like this, that's a kind of expansion. And so why that is, you seen in some other place, and if not, we come to it later. But right now, let's just stick with this. Okay. Okay. So then the question is how good can this, how good or how large can this spectral gap be as a function of t? As a function of t in a family of in an infinite family of graphs. So I fix the degree t. Then I ask you to give me infinitely many graphs, and all of them should have a spectral gap bounded away from zero by some function of t. So then the question is, how large can that function be? Okay. So this turns out that this question, yes. So there are many. Yeah. So a theorem of so the history of this theorem is not very clear to me. Like I think it was proved by different people by under different names also possibly at different times. But the result is this, that that this cannot be much bigger than, so I'll write it informally. Is that this spectral gap is less than t minus 2 times square root b minus 1. So that means that the absolute value of lambda is at most is bigger than 2 times square root of b minus 1. Equivalently, lambda bigger than 2 times square root of b minus 1. Of course, there are some terms here. So plus order smaller of 1. So there are these terms here. So of course, because can you give me an example?
Minus small of 1, right?
Sorry.
Minus minus follow of 1.
Yes. yeah, it dip, yeah, sign doesn't. Yeah. Okay. So of course this doesn't this term has to be there, because can you give me immediately an example of a graph that has spectral gap d of which is of degree d?
Click.
Yeah, just take the clique. So you take the clique, and so just the clique on d+1 vertices, for example, spectral gap. So the top eigenvalue is d, all the other eigenvalues are 0. So, well, actually, that's not quite right. So the way I do this exercise. So, but yeah, for example, take the.
I think the spectral gap is even larger than D, right? Or there are one eigenvalue is D and the other are -1s.
Yeah, other minus. Yeah, so you can do even better. Yes, d+1. So yeah, because you've removed the ID. So okay, so
Sorry,
this,
Piyush, what was the I got a bit confused. So what was the statement again? So Alon Bopana informally states that this spectral gap is at most.
yes. So it's essentially, so up to some small O of one term, which depends upon the size of the graph. It's d minus, it has to be less than d-2 times square root of d-1. In other words, the second largest eigenvalue in absolute value has to be at least 2 times square root d-1.
No, but then you said that for clique
Yeah.
on d+1 vertices.
Yeah, but that's why there's a small O of one term. That's the necessity of that. The bound clicks only in large graphs.
That was the thing. Okay.
Yeah.
Sorry. Yeah.
So the O1 term is important. The same thing you can also, so if you just define the spectrum of the adjacency matrix of the infinite d-regular tree, then also you can get to this 2 times square root of d-1 number quite easily. And in fact, in some way, at least in hindsight, you can claim that one of the proofs of the Alon-Bopana theorem is sort of inspired by this fact that if I take the adjacency matrix of the infinite d-regular tree, so now it's an infinite matrix, whatever that means. And now I ask for and now I start doing some Rayleigh coefficient calculations on it for some reasonable vectors.
Sorry, I got confused again, Piyush. I'm sorry. Yeah. So this little O of 1 with respect to 1, here D is a constant. When you say
D is a constant, D is fixed.
D is fixed.
D is fixed. Yeah.
Okay. So little O of 1 with respect to n, the size of the graph.
Yeah.
Right?
Yeah. So for example, one of their bounds, I think it goes down to 0, so that one term goes to 0 with the diameter of the graph, something. So that's the kind. Okay, so okay, so just I just note that this 2 times square root d-1, this number also comes by looking at the Rayleigh coefficient, the usual Rayleigh coefficient, just the same way you do for finite matrices. For the adjacency matrix, so now it's an infinite adjacency, it's infinite matrix, so you have to be slightly careful in what vectors you apply it to. Matrix of the infinite d-regulatory. Okay. So we have to be careful in what test vectors we can choose. So you can't choose, for example, the all ones test vector, because that's in some sense not even like it's so the vector should have some norm, and now it has a vector with infinitely many coordinates. So you basically should have a norm even then, and then do this calculation.
Sorry, Piyush, can you please recall what is the Rayleigh coefficient?
Oh, Rayleigh coefficient, yeah. So Rayleigh coefficient of of vector U and matrix A is U transpose AU divided by U transpose. So the reason is that, especially for symmetric matrices, you can capture all the eigenvalues by the min-max. So in particular, if U was an eigenvector, this would be exactly the eigenvalue of that eigenvector. And the maximum possible value of this for a symmetric matrix would be the maximum eigenvector. So is this fine?
Yes, yes.
Okay. Yeah, so we will not need this. Yeah. So, but yeah, the point is that this 2 root d minus 1 is not some mysterious number. It is, well, yeah, it is a mysterious number, but it's coming from a reasonable place. And what is now we can say what is a Ramanujan graph. So Ramanujan, so a family, so an infinite. Oh, actually, I think I might have. Yeah, so an infinite family of graphs is said to be a family of Ramanujan graphs of deregular graphs. Family of Ramanujan graphs is for every graph G in the G in the family. Family, this spectral gap of G is bigger than d minus 2 times square root d minus 1 equivalently. Lambda less than 2 times. So remember what is last lambda G? So this is this putting G also. So is this, so you drop the top eigenvalue that you're getting with the all ones eigenvector, and now you have to look at the remaining eigenvalues. Among them, you choose the one with the maximum possible absolute value. So what will this eigenvalue be? It will either be the second largest eigenvalue or the smallest eigenvalue. It has to be one of those. Okay. So note that lambda G is actually is equal to max the absolute value of lambda 2, the second largest eigenvalue, and the smallest one, because the smallest one happens to be negative. Okay. So there are two things here. So one is there's the only parameter in some sense is degree d. So you fix the degree d, and then you are asking for a large family of such graphs, the infinite family of such graphs. That's the game. So there are constructions of such graphs. So the name Ramanujan comes from the fact, I think, okay, so very well. But so some construction of such graphs are number theoretic in nature. So there's a famous conjecture, a famous construction, which which is of degree 3, and it's based on taking GFP and connecting each each element of GFP to its neighbors, like the +1 and -1 neighbors, and its inverse. So it's 3 regular, and so these graphs were shown to be Ramanujan for any prime p, I think, or at least starting prime p. Siddharth probably will remember the names of all the others. So Sarna can do this. Or this is the Margulis. So which one is this? So, yeah. So this is one number theory. The other number theory construction. One is due to Margulis. The other one is due to Sarnak and other. But these are like for specific degrees, because for which they can prove some number theoretic facts. So the question of whether you can get this for any degree d was open for a long time. And in particular, it is known that a random graph is not Ramanujan. So if you pick a random graph of random d-degree graph, it is not, with high probability, it's not a Ramanujan graph. So the usual technique for proving existence does not seem to work for this. So yeah, so the random method of probabilistic method doesn't seem to work, and the number theoretic methods only work for some fixed degrees. So those degrees are infinite, but well, not necessarily. So the degrees are whatever they're, whichever degree, the graph families are infinite, but the degrees are like you can't do it for degree 4 or degree 6 or something. So the goal of this paper was to get this construction, and they do that when for bipartite graphs. So they prove that you can do this with, so they provide a family of bipartite. So this MSS 30. So I show that there exists that for every three, there's infinite family of bipartite. Irregular Ramanujan. So with the same with like what do you call, so both sides of the bipartition have the same number of votes, which I mean which is clear because it's a irregular.
Regular implies that, right?
Yes, that's it. So right, so this is what we do, and the reason for bipartite, the reason this proof will only go as bipartite is what we will do is we'll prove that the lambda 2 is not too large, and in a bipartite graph, the eigenvalues are symmetric.
But then isn't lambda min going to be minus d?
Yeah, so that's the thing. So in a bipartite graph, so you ignore the minus d also, and you look at lambda 2, and that captures the bipartite expansion.
Yeah.
So in a general graph, what I said was fine, that you have to do this d minus d, but yeah.
Why can you ignore the minus d?
So yeah, so this this minus d comes from a very strange kind of a thing. It comes from those eigenvectors which are 1 on one side. So I think it will be like +1 on one side and -1 on the other side, that kind of eigenvectors. So they don't actually affect your connectivity arguments.
So one thing I wanted to say is actually even for a general graph, if you are only interested in the Cheeger-like inequalities, this is, you just need one side of the spectral gap, that is lambda 2g. If you are interested in expander mixing lemma kind of statements, then you need
Yeah,
both
both
sides.
sides. Yeah, yeah.
So in a bipartite graph, since you sort of measure expansion by taking something on the left and then something on the
Yeah.
right,
Mm-hmm.
it's okay to
Yeah, yeah. So that's yeah. So that's the
Hey, expander mixing lemma also works for bipartite graphs, right? With lambda 2 instead of lambda.
no. So what that is saying is that this. So earlier I made a lot of song and dance about taking the max. You drop the first and then take the remaining value. So take the among the remaining values, take the one of the maximum possible absolute. Now in a bipartite graph, there is a minus d also, which comes from this eigenvector, which is +1 on one side and the -1 on the other side. So that eigenvector has eigenvalue minus d. It just flips because when you apply the urgency matrix, it just flips. So, but that doesn't affect us in some sense because for connectivity, this will not give connect. So comparing bipartite.
So basically, you're saying in the definition of spectral gap,
Yeah,
you can ignore this
minus d. Yeah.
minus d.
Yeah,
because-
but I cannot ignore top. If there is a double eigenvalue at d, that I cannot ignore.
Correct. So combinatorial expansion somehow doesn't get bothered by.
Yeah, the minus d. Yeah.
Okay.
Mm-hmm. Yeah, and so the crucial thing here that here for the bipartite case, yes, it is enough to prove lambda 2 less than 2 times square root d minus 1 because of two reasons. Because one, the eigenvalue at minus d does not affect connectivity concerns, and lambda min will be equal to minus lambda 2. So so the point is that the symmetric of a the spectrum of, so if so so let me actually make this point because this also is implicitly using what it is. The spectrum of a bipartite graph symmetric about 0 if if lambda is an eigen of a let me say deregular bipartite graph. If lambda is an eigenvector, is an eigenvalue, so is minus lambda. So lambda 2, so the lambda min on the left hand side that comes to the negative side will exactly be equal to minus lambda 2. So you just so just getting a bond lambda 2 is good enough because of this. So why is the first point true? Why is the first point true?
That's, I mean, if you can just always invert the eigenvector on one
Invert
part.
the signs of the left side and the lambda will get reversed.
Yes, but why is that possible? That is possible because the matrix, the adjacency matrix of
It looks like a block matrix where the
Yeah.
top right and bottom left halves have zeros everywhere.
Yes, so it looks exactly like this. So one follows because the adjacency after a suitable permutation of the word, after like permuting the rows and columns of the word, after a permutation, the adjacency matrix of such adjacency matrix of a deregular matrix deregular.
You don't even need any deregularity for this, right? This is
No, you just need that the two sides are the same size. That's all.
what has the same side?
Like, I mean,
The partite
m,
set?
yeah, that you need
No,
to.
I think, I mean, but isn't it clear? Like, I mean, if you just invert the sign on one partite set, why do you even need the sizes to be the same? It just
Oh, even yeah, maybe that also works. Let's see. So,
yeah.
so let me
Just
let me just do the argument. So,
yeah.
so, right. So, one follows because what is this? So, yeah. So usually, so it's so yeah. So it will look like this. A and A is no. A transpose, right? Okay. And so if you have UV,
Then
is equal
uv is an
to,
eigenvector with lambda. Then u minus v is an eigenvector with minus lambda.
yeah. So then and then actually you just need that. Yeah. So minus V is equal to minus AV A transpose V, which is, we know that, so, but this has to be equal to AV A transpose U, A transpose U, yeah. So AV is equal to lambda U, so this is minus lambda U, and AT transpose U is just lambda V, so this is lambda V, so this is minus lambda U naught. So for any bipartite graph. So that's it. So that's it. The only thing we need is another. That's all. Okay. Okay. So good. So yeah. So our goal now is to establish bounds on the like on this lambda 2 for these bipartite. So so the method for so the technique for doing this was developed by Bill and Linear, called, and it is called two lifts. So that, what is the idea? So the idea is that somehow you start with a graph that is already Ramanujan in some sense. So it has good spectral gap. So what is such a graph? The clique.
Bilu and who?
Linear, nothing linear. Yeah. So what they want to do is to come up with an operation that you take a graph which has good spectral gap, and you double the number of vertices, and somehow get a graph which still has good spectral gap. So two lift is such an operation that potentially can do this. So what is this two lift? So it's given a graph G, given G. So there are many two lifts, and a two lift will be a graph twice as many edges and vertices. Edges and vertices at G. Constructed as follows. So every vertex now has two copies. So we can call them V up and V down, or V0. Let's call them V plus 1 and okay, let's call them V. Whichever. So V plus and V minus. Okay. And for every edge, this is now a choice. So every edge you have to make one of two choices. For every edge, U, comma V, G, for each edge, choose one of the following. So which are the two things? So first one is that you just connect U plus to V plus and U minus to V minus, or flip, where you connect U plus to V minus and U minus. It's not like you do the same thing for every edge. For each is separately. So separately for each edge, separately for each edge. Okay.
Piyush, I'm not able to understand this point too. You are saying that for each edge,
Yeah.
I have to choose one. So that means for every choice, I'll get one different
Yeah.
graph.
Yes. So we have 2 to the power the size of edges, many different possible two lips.
Okay.
So yeah. So number of possible two lips is 2 to the power, because you have two choices for each, two independent choices for each edge.
Some of them will be isomorphic, right?
Yeah, but
We're
that's
not
fine.
counting.
We are counting everything. Yeah. So, right now we're counting everything. Okay. So this so these are the number. These are all the two lips. And notice that if the graph G was deregular, this is also deregular. Okay. And as I said, the number of vertices, number of edges is exactly twice. So some two lifts are completely trivial, right? So there's one particular two lift, for example, which is just two disjoint copies of the graph. If you put the plus, so this equal equal lift on every edge, it's just some trivial thing. It has done nothing. But the point is that if these two things are done together, they might construct more interesting graphs. Okay. So why is this useful? So let us at least see what is the spectrum of this new graph. So we can index each two lift by a vector.
So, Piyush, here I guess because you want this such a tight spectral gap, I mean, it's an alternate suggestion to using this zigzag walk or something, right? To blow up the vertices of the graph while preserving spectral gap even.
Yeah, but here
more
there's not even no blow up happening, right? So the degrees are not changing. Nothing is sort of changing, and sometimes it can do weird things, right? Like it can just create two copies. So, okay, I'm not sure, but the idea roughly, I think, is yeah. So
Yeah,
I
like
mean, yeah.
I was trying to put it in context with the zigzag thing. That also you start with a very good graph and you
Yeah. So, but here though it's like, so the zigzag thing sort of just like it works with high probability kind of thing. So it's like even more that you.
no, but that is like a deterministic thing almost.
Yes,
Yeah,
it just works, and here it will be like most of them don't work.
oh, okay.
Most two lifts don't work.
I see. Okay.
At least don't work to give you the full Ramanujan thing. So,
Sorry, Piyush, I had gotten distracted. Most two lifts don't work, meaning. So
they
you're
won't.
saying a two lift to be like as you said, there are 2 to the cardinality of edges, many lifts.
Yeah.
Each one of these you are calling R2 lift, is it?
Yes, yes.
Okay.
So let's say you choose one at random and then see if high probability it's keep doing this, and is it preserving the spectrum with high probability?
Yes.
So this doesn't seem to work. Bilu and lineal got some bound that was d log cube t something. So this is a large factor in front. Yeah, but we'll see. But first, let's see why the 2 lift. At least it behaves very nicely with respect to the spectrum. So let's index each 2 lift by vector in +1 -1 e. And what is this thing? So we just call this as a plus lift, and this as a minus. So for each edge, if it is the flip, then you call it minus. If it's this one, we call it plus. This thing, why this will become clear from some time. Okay, so yeah. So now what? So let's see. So what is the yeah. So now we want to look at the spectrum of, yes, we want to. Spectrum of this 2 lift. So let's call this GS. This is which is the S2 lift of G. S is an element of -1. In terms of, so let's look at what is the agency matrix. What does the adjacency matrix of GS look like? So what is, so suppose, so I have the adjacency matrix of G, right? So here is the A is the adjacency matrix.
Are you assuming G to be bipartite now, or
No, right now I'm just doing it for arbitrary graphs. So G is, so A is this matrix. So what does this mean? So like I can take this I and J, and here, so one, like if the, so H I J is present, 0 otherwise, right? So that's what this matrix looks like. Now, what is the adjacency matrix of GX, of GS? So if you think about it, what is happening is the following: that I can do it. I can get it by replacing each entry of A by a 2x2 block matrix, and that block matrix is what? It is either identity or the flip. So
anti-identity?
yeah, it's called the X matrix, right? If you the physics
Sigma X.
so
Quantum business, yeah.
yeah. So where B is equal to I 2x2, which is just 1 1 0 0. If S of ij is yeah, so basically this also depends upon the convention. So I'm assigning some vertices to plus, some vertices to minus. So flip that convention, then these I and X also change. But I have fixed the convention on which vertices have been called plus, which vertices have been called minus. And so the assumption here is that each I now becomes so this corresponds to I plus, I minus, and this corresponds to J plus and J minus. So that's a blow up into. So if this Sij, in this flip, the sign vector denoting the flip, if Sij is equal to 1, then this is what it is, and it is equal to X 2 plus 2. Right. If S Okay, so this is a complete description of the adjacency matrix, right? Is this fine?
Yes.
Okay, good. So now let's try to see what is so let me also write it in a slightly different way, which will be easier to think about when doing some calculations. So this means that adjacency of GS can be written as summation of Eij tensored with, and I'll say what Eij is, tensored with the
Eij is just containing the edge. The
sorry.
Eij is just the matrix with all zeros and it has a 1.
Yeah, or the Ij and Gi. Yeah, so the only thing is it's Ij and Gi because
Ij and Gi, right?
Yeah,
right.
yeah. So and so what is this? So this is basically 1 plus J 1 minus Si2. Right. So it's so it's basically 1 when Sij is -1 and 0 when it is 1.
For some reason, this reminds me very much of XOR lifting in the case of Boolean functions.
So XOR lifting. So
anyway, we can talk later. I mean,
but yeah. So these things are So I don't know what XOR lifting exactly is, but
I mean, like XOR lifting is like, you have a Boolean function F, base function, in communication complexity.
Yeah.
Right. And now, I mean, now it seems it should be. That is where we probably got the name lifting from.
No, lifting, I think maybe comes. Yes, in this, I don't know. So which one? So
you have this
topology or something.
Yeah. But basically, like you have a function F, and then anyway, you sort of each input bit to F is replaced by an XOR, right, of two independent bits. And this gives you a family of functions.
Exactly. So that. Yes. Here is some deterministic thing, and you'll be choosing one as in the end. So the goal will be to find
right.
But right now, this is what it is. Okay. So okay, good. So but now we can start thinking of this spectrum. So why? Because let's say suppose U is an eigenvector, U belonging to R n cross n is an eigenvector for G with
how can U be in R n cross R n?
Yeah. It's an eigenvector for G with eigenvalue lambda. Then I claim that this is still eigenvector of this new matrix with the same eigenvalue. Why? Now consider this. So consider this U tensored with the.
But Piyush, wait, there is a type mismatch. No, U is an R to the n.
Yeah.
Now your lifted matrix.
Yes.
Is over 2n cross 2n.
Yeah. So that's why I did it. So now consider this vector, which is this U tensored with 1 1. So what is that? What does that look like? So that looks like U1 U1, U2 U2, U3 U3, so on to U. Okay? So let's look at what this adjacency matrix does to this. So then this ADG of GS on U tensored 1 1. So yeah, so this you have to just check that what I'm doing is correct. So this becomes exactly summation over Ij in Eij times U tensored the X or the identity matrix applied to 1, but the all 1 vector is a eigenvector with eigenvalue 1 for both those matrices. Right? So this thing is just 1, 1. But then this just becomes exactly AU tensor 1, 1. So this is just lambda. So we already got the full spectrum of A sits inside the spectrum of ADGGS. Okay, so this is always there. So spectrum of A with multiplicity also sits inside. In fact, more, right? Even the eigenvectors sit inside.
The rest are all zeros, the remaining eigenvalues.
No, that's the point. So this is where the interesting thing comes in. So now, so the new ones will sort of depend upon. So these ones didn't depend upon S, right? And the new ones will depend upon S. So the question is, what are these eigenvalues? They are not zeros; they are something else. And the question, so our whole goal will be to find an S for which these ones are nice. So
Piyush,
Mhm.
like one thing I'm not able. So what happens if I just like take a vector which is on some v plus and v minus? It's 1 and 1.
sorry.
So I'm taking a vector. Oh, okay,
Mhm.
okay. Sorry. No, I misunderstood.
Mhm.
You. No, it's okay. Okay, go
Mhm.
ahead. Yeah.
So now, okay. So what about the remaining eigenvectors? So now this is where the main construction comes in. So now consider this matrix AS. Consider the matrix AS, which is n cross n. And what is this matrix AS? So AS is defined by summation this Eij, but now you multiply by the sign of Ij. So it's almost like an adjacency matrix, except you put the sign of the left. Okay. So it is still symmetric. Okay? So each edge appears with its sign. So AS is also symmetric, right? And it also has its own. So therefore, it's symmetric. So it has its full collection of eigenvectors spanning the whole space. So let it and therefore has a spanning set of spanning eigensystem, right? Like eigenvectors and eigenvalues. Eigensystem. So let me call this new one, or rather mu I vi. I goes from 1 to n. Vi is orthonormal. And mu I is a real. Okay. And now let's so now you can guess what the other eigenvectors are, right? So consider the vector vi tensor 1 minus 1. Okay. So what is this?
So if Sijs were all +1, you got the entire those eigenvalues, is it? Like the original ones?
Yes. So if all of them are +1, then I just get the same thing twice.
Right.
That's what you're going to see.
Right.
Okay. So now let's look at what the ADG of G does to GS does to this vector. So again, I can apply the tensor decomposition thing, and so I get that it is Eij times Vi. So let me call this something else. So let's call this Vk. So summation Ij is an edge. Tensor. Now this is the interesting thing. So what is this now? So if it is the identity, then everything is an eigenvector of identity with eigenvalue 1. So that is +1, 1 minus 1. But if it is x, then this 1 minus 1 becomes minus 1, 1. So it just becomes multiplied by -1. So what is here? It's exactly 1 minus 1. except that you get to multiply by Sij, because exactly at those places do you have Xij. Right? And so this is equal to AS VK tensor 1 minus 1, which is exactly mu k VK tensor 1 minus 1. So now we have constructed, so now we have, so, and notice that all these new eigenvalues, eigenvectors are orthogonal to the previous ones. Because, why?
The dot
Why?
product are 0 because just look, the components for UI cancel out.
Yeah, I mean, just look at the second component, right? So note that U tensor 1 1 inner product with VK tensor 1 minus 1 is exactly U inner product VK times 1 1 inner product 1 minus 1, which is 0. So we have, so we get that spectrum of ADG of GS is exactly the spectrum of a union spectrum. And here it is, so this is said to be supposed to be like multi-set union, right? I mean, with multiplicities. This is like a multi-set union. Okay.
No, the union is over.
No, multi-set. So basically, spectrum of A might have some multiplicity, like some eigenvalues might apply 2 times. So I will count them. Like I will say, okay, lambda appears twice here, thrice here, so it appears 5 times in the union. That. I mean, just the usual way we count spectrum. Right? So we always count things with multiplicity. So that's that's what. So these are called the new. So I think yes, these are called the new eigenvalues. Right? So the original, some eigenvalues are already there, and now some new ones have been introduced by assigning.
But I guess you want to somehow, I don't know, I'm just thinking that,
Yeah.
you know, I mean, you're doing this 2 lifts in the hopes of controlling or amplifying the gap in some way, right?
No, we are not amplifying. We just want to preserve right now.
Just want to preserve. Oh, because you want an infinite family, is it?
Yeah. So all I want, I start with the complete graph, which already has as good a gap as you can ever hope for, much better than. And then all I want to say is that one of these ASs still has a gap.
Correct.
And then after that, again, I'll do again the lift and say.
Got it.
So in fact, now we have gotten to the point that in the bipartite case, all we have to show is that. So.
Piyush, is this an existential result or a constructive result?
So the original result is existential. Later papers have, I think, made it constructive.
Oh, okay.
Yes. So in fact, it's a different kind of proof of. Yes, it's not a probabilistic method. So it will be nice. So we have to prove. So it's sufficient to prove. It is sufficient to prove that if A is the adjacency matrix of a deregular. So now the 2 lifts is also gone. The only thing that remains is this assigning signs to edges. For deregular graph G, then there exists an assignment of signs. And an assignment of signs to the edges of G itself, such that the corresponding this AS, like the maximum value of A, is less than 2 times 15. So this will imply the existence of an infinite family of T regular pi.
So Piyush, 1 second. So this lambda max by definition is the second largest eigenvalue.
No. I just mean lambda max. Exactly.
Like the real.
Yeah, the largest eigenvalue.
Yeah,
That's
yeah.
it.
Then it's okay. Then it's okay.
Yeah. So bipartite. So the bipartiteness will not come into this part. The bipartiteness only comes in the previous. So the bipartiteness was only used in the bipartiteness was only used in the above reduction, like the.
Oh, you mean this claim about this AS will continue to hold for any A?
Yes.
Oh,
yes.
wow.
The above reduction to lambda max, the claim about the.
Where did we use bipartiteness?
Well, where we say that we only have to care about the maximum eigenvalue, we don't have to care about this minimum, the minimum with possibly negative sign.
But right now you just showed the
symmetric
Union result seemed to be true for anything, right?
Yeah, that's fine. But we before that, right? We already made our problem simple by saying that we'll only worry about the maximum, the second largest eigenvalue of these graphs. Okay. And
so in a non-bipartite graph, you would have to bound both lambda max and lambda mean of AS.
Yes. Yeah, and now we don't have to do that because we already said that the minus D eigenvalue doesn't matter, and others are symmetric around the origin. So everything is symmetric at the origin, and the minus D one doesn't matter. So all we have to do is to show the second largest eigenvalue is at most 2 times square root delta minus 1. But now we are saying that the second largest eigenvalue will just come from A. So whatever is the new things that are coming should not go beyond this 2 times square root D minus 1. That's all.
But you had said that we will start with KD. So
yeah, that's good.
What
is KDD?
So yeah, KDD.
We could have started with KDD if we had the full result, but now okay. So if you started with KD and you did all this argument, you will get an infinite family of graph where lambda 2 is always at most 2 times square root of D minus 1. But you have no guarantee on what is happening on lambda min in the proof so far. Okay. But if you start with a bipartite graph like KDD and then run this whole thing, then you have a guarantee because of the symmetry.
Okay. And the point, I guess, also is that bipartiteness gets preserved by two lifts.
Yes, that is true. Yeah.
Okay.
Yeah. So just a note. Maybe I should put these things a note. We will start the two lift process.
Sorry, a stupid question. So, I mean, therefore, you're saying to prove this AS business, you will have, because once you prove that, you will prove the Ramanujan conjecture, whatever that conjecture, right?
With bipartite graphs, yeah.
Yeah, with bipartite, but you will prove that conjecture.
Yes. So all I have to show is that there is some signing for which this is true. Yeah, for every graph. But the point is, the random signings don't seem to work. That's the problem. With high, so I think Bilu and linear, I haven't looked at it, but I think what they showed that If you do random signings, then with high probability, you get something which is like square root d times, then there's a polylog factor. And there's a constant also in front. So it's not 2 times square root d minus 1, some c times square root d times some polylog factor. Something. Along with the same.
That was the result of Bilu and linear.
Yes. But they came up, I think, as far as I know, I think they came up with this idea of using two lifts. And
They came up with what?
With this idea of using two lifts.
Huh?
Of using two lifts.
Or two lifts. The idea of using two lifts. So
Yeah.
the two lift I was not able to. Okay.
Yeah, yes. Yeah.
The idea of using two lifts. Okay.
Yeah. Bipartiteness, along with about AS. Then ensure that at every stage we have spectrum bigger than 20 minus 2 times, which is actually it's also square root d minus 1. Square root d minus 1 plus minus 1 whole square. Yeah. Okay. So now we have to prove this. So this is the claim to be. So this is the A is certain symmetry for d delta G, and there is this nesting sign space of G such that lambda max X less than 2. Okay, so let me just do one calculation that might look completely unmotivated in the beginning, and we'll stop there, and then we'll continue next time. But this completely unmotivated calculation will actually connect to something we've done before. So,
but just one thing.
yeah.
So you're saying that this all this MSS is about proving this claim.
Yes. Okay, so let's try to use the probabilistic method. I've been bad mouthing the probabilistic method throughout the class, but let's try to use it. So what is this lambda max? It's the maximum root of a polynomial, right? The characteristic polynomial of AS. So lambda max AS is exactly the max root of what? Of this characteristic polynomial of AS. So X, which is just nothing but right. Actually, I think okay, this is pretty easy. Okay, but okay, so let's look at. So why not first let's look at what is the expected, what is this expectation of this polynomial. So that's why it might sound completely unmotivated. So what is this expectation of det xi minus AX? Okay, what is expectation over what? When S is uniformly at random from -1 to the edges. Yeah.
Piyush, just to get a gauge of things. So if instead I was dealing with with a completely random plus minus 1 matrix, is this easier to see? Like, is this almost like just
What is
standard
what
concentration bounds?
which
Like, so if I instead said that AS is like every entry I can set it to be plus minus 1 independently.
no, then it's like then yeah, then of course people know a lot about the eigenvalue distribution of plus minus 1 random matrices, but it's not going to be Ramanujan.
Oh, it's
Well, it's
still
not.
that concentration will still not be enough to get you this 2 square root t. Like, I'm just
No.
okay.
Yeah. So see, I think in particular, I think it. So depending upon how you do it, so certainly it's okay. So this I think is known. It's a rigorous result that a random graph is not Ramanujan.
Okay.
I don't remember that. I don't
I
remember
feel
the
it's almost Ramanujan. Right?
Yeah, it's almost, but not. Yeah, but it is. So
Plus
it's like
mod of 1.
yeah. So it has a it has a plus. It is above on the threshold always.
No, but Piyush, I'm a bit confused by this question. Siddharth's question, from what I understood, was each entry of the matrix n cross n matrix is being randomly assigned. I mean, you start from the all ones matrix and then choose 1 minus 1 at random.
Yeah.
Yeah, isn't that what you said, Siddharth?
Yeah.
Yeah.
And then possibly normalize, etc., to make things.
No, but when you look at when you're saying so it's a stupid question, I realize, because when you're saying that if you look at a random graph, the random graph's adjacency matrix has zeros as well, right? I mean, the non-edges are zeros.
So that I was just saying that like these random constructions are not known to work. That's
including the one he's suggesting, which is not quite the random graph.
Yeah, that one is very well understood, but I think it just doesn't give the Ramanujan thing. And as Shriyata was pointing out, this Friedman, I think Friedman's is that yeah. So there's a paper which shows that random graphs are almost there, but not quite there. So they will not fall below the Ramanujan threshold, like this construction would. Okay. So let's just do this computation and see what it is. Okay. So I think this computation. So I don't remember who did it first. I think it was first done by Gottsel. But if you put your mind to it, you can do it, and it's and this proof is also there in the MSS paper. But yeah, it's not hard. So let's just do it. So what is this? So what is this first? What is this determinant of xi minus as? So it is you have to go over all so just right all permutations and look at the sign of the permutation, and then go over I going from 1 to n, and then you have as I sigma n. Right? This is just the definition. Sorry, this is for the usual, like this is the determinant of m. Right? That's the usual definition. But now I'm looking at determinant of xi minus as. Notice that importantly, as has zero diagonal, right? Because we only had it's a simple graph, right? So there's nothing on the diagonal. So it makes sense to partition this these sigmas based on where their fixed points are. So I go over all subsets of n, and then I go over all those sigma in n such that the fixed point of sigma is exactly s. Okay? So these are exactly the fixed points. And then I ask, okay, then I put, okay, so sine of sigma, I going from 1 to m, and then I have xi minus as, and of this thing I am putting sigma. But what are the so the s entries are pretty clear, right? So the s entries are exactly just x, because there's nothing on the diagonal of as, right? So this becomes s subset of n, and x to the power the size of s, and then I'm going over sigma in n. And if I am putting fixed point of sigma equal to s, I might as well go to sigma of this so let me maybe s will be confusing. Let's put t. Sigma the permutation group of the permutations of everything except t. because anyway everything in T is fixed. And the sign of that permutation is exactly the same as the sign of the original permutation, because fixed points don't contribute to the sign. And then what I have is, on that part I don't have fixed point. So on that part I just have AS times I sigma I.
So this sum should be over non-fixed points in n minus t, right? Like non-fixed derangements. Derangements.
Yeah.
Yes, yeah, derangements. Yeah. But okay, I mean I can put all of them also, because if why can I put all of them? That's a good question. So why can
Otherwise it will zero. No, when the
yeah, exactly, because A has nothing on the diagonal, so I can put if I can put the non-derangements also, they will anyway cancel out. So I have basically doing two steps in this. So where this last step is, and this is actually a bit wrong, because I have to also put the minus sign, right? So there's a minus 1 to the power whatever so there's also so there's a minus 1 to the power n minus the size of t or something. This AS comes with that sign. So let me just write this. So this whole thing is now t subset of n x to the t minus 1 to the power n minus t, and then here you have sigma on sim. So what is really there is just the determinant. Yeah, okay. So it's actually just a determinant, but let's write it. So sim n minus t of sine sigma and product as as I sigma I n. So now the question is, what is this? Which permutations can even so okay, so this so far that's fine. So far nothing. Good. Now, but notice that we had to do some expectation, right? So this was just det xi minus as, and there was what we wanted to compute was the expectation of this over this random signing of s. So now we have reduced ourselves to computing expectations of these guys, because these parts are fixed, right? So we have to compute. So given a t, so given t subset of n, we want to compute exactly the expectation of the determinant of as restricted to restricted to t, right? So that's exactly what this thing is. I mean, w when s is uniformly attractive. Yeah, so this translation is that w is exactly n minus t. Yeah, that's it. And this is just a determinant. But okay, so but notice what is this? So what kind of sigmas are allowed? So
Only the involutions will survive.
yeah, so yeah, exactly. So that's the whole point. To take any sigma and let's see, well, can this expectation survive? So the expectation. So notice that now this. So of course, if any sigma I better be a neighbor of I, right? Otherwise, anyway, the term will go away because that term is 0, right? So let's just see what the conditions are. So for the expectation to survive, for sigma to survive, we need 1, I should be a neighbor of sigma I for every I. Otherwise, it's just zeros out. But notice that if sigma I equals I, then we should also have sigma equal to j, then we should also have, we must also have sigma j equal to I. Why is this? So suppose not, then that corresponding this Rademacher variable will appear with power 1 in this term. So notice that the Rademacher variable for the edge ij appears for the ij entry and ji entry. And if it appears only once, then the term is gone because they are independent signs. Right? So this is exactly right. So is that fine? So it better be that if I sigma is appearing, then sigma I also appear. Okay. So so that's what Shweta was saying. That all the sigmas that are allowed must be involutions. So they must be inverses of each other. So they must exactly be products of disjoint cycles, disjoint two cycles. So I goes to sigma I goes to y, then some other, so in pairs. But what are these objects called?
Involutions.
No, in a graph theoretic sense. If
Matching.
I have,
Matching.
yeah, so it's exactly a perfect matching of this graph. You have to match in fact every vertex.
No, there could be 6 points also, right? Sigma equal to I.
No, why? How can there be a 6 point? Suppose there's a fixed point, then what happens?
Okay, again it can.
Fixed point goes away, right? Because it's 0.
Yes.
So by the first point. So these sigmas correspond to, so the surviving sigmas. So exactly those sigma survive that correspond to perfect matching.
So this is almost looking like the matching polynomial.
It is the matching polynomial. That's the point. So that was I did this calculation. Matchings of the graph restricted to W. Okay, and
Except
then
maybe there's a 1 by x substitution somewhere because that
it's one of the several matching polynomials to look at.
yeah.
So yeah, so and then what is the sign of this? So each involution contributes 1 exactly to the sign. So the sign of this is exactly the 1 minus 1 to the power the number of to the size of the matching. So and sine sigma is exactly equal to minus 1 to the power. So with all this we get that this expectation is UA n of this chi of AS in X is exactly summation over all subsets S over all subsets S of B X to the power size of S. Then there was let's keep track of signs minus 1 to the power n minus the size of S, and then what was remaining is exactly minus 1 to the power the size of sum over all m such that m matches all vertices in V minus S of minus 1 to the power n, which is the same thing as m matching of V minus 1 to the power m. There's a minus 1 to the power n also, and minus x to the power n minus 2 times the size of n, because that's exactly what is the size of x. This, if I think this is our usual matching polynomial evaluated minus x up to minus 1 factor. Okay, so recall that.
So I'm a bit confused. So here, I mean, we haven't yet looked at the expectation, right?
No, we did. That's how we got to.
Oh yeah, we did.
That's how we got to matchings.
Yeah.
So the expected polynomial is the matching polynomial, and why is that good? The expected polynomial has the right property. Its maximum roots is exactly 2 times. It has at most 2 times root b minus 1, right? So the expected. So by Heilmann-Lee, expected chi of ASX has roots, has maximum root at most 2 times root t minus 1, which is what we want to do for one of the ASs. And the next time we will look at how to get it.
So, Piyush, here, like one thing is already there, that we didn't actually need full independence of the signs, just that every neighbor should see an independent sign assignment marginally. Because every time you get a free
No, not
free
right.
radical.
So because it's not. Yeah. So, but yeah, that is exactly where you use that it is independent of all the other signs. No?
Yeah, but for that, all you need is that there is independence.
This is exactly.
Do you need
So
full
you're exactly
independence?
doing Fourier analysis kind of thing, like Boolean function Fourier analysis. So I think you need the. I mean, yeah, you need almost everything, right? I mean, all the way up. I mean, that moment has to be zero.
If they are not fully independent, then a permutation will be product of several cycles. So can you split the product, the expectation of the product as product of expectations if they are not fully independent?
No, yeah. So in general, no. So I think yes. In this case, you more or less need the full independence. I think. I mean, or at least up to the moment of up to the size of the maximum match or something.
Okay.
So sorry, Piyush, but then you're saying I'm confused. So you're saying this shows the expectation is the matching polynomial, and we have already proven, as you said, right? It has maximum root.
Yeah.
At most this.
Yeah.
Uh,
So now we have to say that one of the polynomials. So if you take expectation of polynomials and the maximum root is something, then one of the polynomials also has the same thing. This is false.
okay.
So yeah, so you have to figure out a way to do it. So it is true under a certain setting, which is with this so-called interlacing. So that's the next thing we look at.
Sorry, it is what is true?
So if the polynomials that you are taking expectations over, so the expectation doesn't matter. It's more like a sum of polynomials. Right? We can forget about the weights because sum is what matters. So you have a sum of polynomials, and these polynomials, the sum has a maximum root. We want to say that at least one of the summits also has a maximum root at most that much.
Correct.
So this is not true in general. It's easy to construct counterexamples.
Right. But you want to say if the
if these polynomials that you are summing have a certain property, if they are somehow related to each other in a certain way, which is called interlacing. Basically, if they are all real rooted and the roots are sort of interlaced by a common set of numbers. So interlacing means exactly what you think it means. It's like, so you have a root. I say a set of numbers interlaces the roots. If all the roots so between every two roots there is one of those numbers. So if I have n roots, a set of n minus 1 numbers interlaces those n roots. If between two adjacent roots there is one of those numbers. Okay. So if there's a common such vector that interlaces the roots of all of these polynomials at once, then you can do it. So then the question will be, how do you find such, how do you prove that there's a common interface? That's where the stability theory will come in.